All right, 1.1 is all about problem solving, and we had looked at some basic ideas about how we think through problems last time. We talked about understanding the problem and thinking through it, devising a plan to follow it. This kind of list is kind of where we're going to focus our attention today on some different strategies and how we can utilize them. Carrying out our plan, like actually doing what we thought we were going to try and do to solve a problem. And then checking our work, both intuitively, like as in does it sort of make sense, and sometimes concretely, do the numbers actually check out? So that's what we had finished last time. And we're going to start today with a guy whose name is Gauss. Gauss is actually a pretty famous mathematician. I'm sure you've never heard of him, which is totally fine. But in mathematics world, he's pretty important guy. And just like everybody, he was once a child. And when he was a child, this legit happened in his classroom. He was about 6 years old, first grade. And his teacher gave him an assignment, the whole class an assignment that was supposed to take them a lot of time to do. She said she wanted him to add up the numbers from 1 to 100. Now, that should take most 6-year-olds quite a time to do, right? Unfortunately, for the teacher, Gauss wasn't most 6-year-olds, and it did not take him very much time to do. So what I'd like to show you is the strategy that Gauss, legit, as a 6-year-old used to figure out how to do this problem much more quickly. And it's a clever strategy, and we can use it to find other like summations like this very quickly as well. And by very quickly, that's a relative phrase, right? What I mean is we're not actually going to add 1 plus 2 and then plus 3 and then plus 4 and then plus 5, which would take very long, agreed? We're not doing it like that. Okay, but what we are going to do to start with is we're going to write out what it is that we were asked to do. Namely, we were asked to add the numbers from 1 to 100 up. Now, I'm not going to write all of them down, but I'm going to write down the first 3 and the last 3 just to develop a sense of what's going on here. And I'm just going to put a ... in the middle. So then I have 98, 99, and 100. And for the purposes of keeping our work organized so that we have something to call it as we're working it together especially, I'm going to give this summation a name, and I'm just going to call it S. S for summation. So this total, whatever it is what I'm going to call S. Everybody good so far? Okay. What we're going to do next is we're going to take this list of numbers and we're going to flip it around and write it underneath itself. Something very clever is going to happen in a moment, but that's what we're going to do. We're going to write the numbers in reverse order. And we're going to add them down. Now notice this is the same list, so it's the same S. So what is 1 plus 100? 101. What's 2 plus 99? 101. What's 3 plus 98? 101. In fact, every single number in this list is 101. Now that's very clever. And you might be looking at that and saying, okay, but it's still just you're adding 101 together a bunch of times instead of adding 1, 2, 3, 4 all the way to 100. Why is that better? It's a lot easier to add the number that's its same number to itself than to add different numbers. In fact, you have a shorthand notation that you learned in 3rd grade on how to repeatedly add the same number together over and over and over again. Do you remember what it's called? Multiplication. Right? You did. So we have 101 plus 101 plus 101. And the question is, how many 101s are there? How many are there? Close. No. There's 100 of them. Right? Every single number in this list is there. There's 100 of them. Now, the 50 is going to come about in a minute. We are going to see something happen with a 50, so you're probably already a step ahead of me. But there's really 100 numbers in this list. Agreed? Okay. So if I'm adding 101 together 100 times, and we've already established that that idea is the idea of multiplication, how can I do that more efficiently than literally adding 101 plus 101 plus 100? How can I do that with multiplication?
101 times 100.
Yeah. I would do 101 times 100. Now, I would like to point out that this is not equal to S anymore. Any idea what it's equal to? 2S. I added S and S together, and I got 2S. So this is double, right? The idea is that this is double what I started with. It's double because I added it to itself. Right? I added all the numbers in there twice instead of just adding them in there once. So then, what is 101 times 100? Yeah.
So, just theoretically, if you multiplied it by 50 instead of 100, would you just get X?
Yeah. The reason I don't want to focus too much on it being 50 is because this works really nicely when there's an even number of them, and it doesn't work so nicely to think about it that way when there's an odd number of numbers. I think my other example is going to have an odd number, and you'd see sort of why there's a run into a problem if we think of it too quickly that way.
Okay.
Yeah. 101 times 100. Did you guys get it? 10,100. But that's double what I'm really looking for. So how do I find what I'm really looking for? You divide by 2. And that's why multiplying it by 50 would have given us the same thing for those of you who are thinking down that line to start with. What is 10,100 divided by 2? 5,050. Now, did Gauss write this all down? He actually probably didn't. He was a very bright young man. I mean, like he was. He ends up being brilliant, does all this stuff in advanced mathematics later. Crazy, crazy smart guy. But this is the basic idea of what he did, is he noticed there was a pattern that would be established if he simply reversed the numbers. Another way that we sometimes will see this explained, and I think your book explains it in this way, is that, so if I write the numbers like this, it'll fit into your plus 50 idea better for the couple of you that were seeing it that way. 97, 98, 99, 100. And so if we add these together and we add these together and we add these together, we get 101 every time. And how many pairings of numbers are there? There's 50. So that's along the same idea. So it's the same process, but a little bit different picture of how you're doing it. Okay. So I'm not trying to confuse the issue. I just want you to recognize that there is more than one way to do the same thing here. Now, this is a related problem. So one of our strategies is to use a related problem to do a problem you already know. If you already have some strategies involved, you don't have to reinvent the wheel every single time, right? Now, you may still find a more clever way of doing a problem, and that's fine. But if you do know a way to do something and you can tweak it, use that to your advantage. This is a similar problem, right? I mean, it doesn't start at 1 and it doesn't end at 100, right? It starts at 36 and it ends at 147. But it's a similar idea, yeah? Okay, so we're going to solve it in the same approach because we have already established an option that worked. So we're going to call this sum S again. So what did we do before? We flipped it around. So we're going to start with 147 over here, and then we have 146 all the way over to 37 and, 36. So I'm going to add vertically again. So what is 147 and 36? 183. So instead of a bunch of 101s, I'm going to have a bunch of 183s, right? They're all going to be 183s. I need to know how many of them there are. So any guesses as to how we could figure out how many of them there are? Yep, Caleb?
147 minus 36.
You were really close, and that's the answer everybody always gives. So you're right on track. Any idea? So you said 147 minus 36, right? Any idea why this wouldn't work? But let me actually go back to our previous example to see if you can see why. Okay, so the general idea everybody wants to do is to take the ending number and subtract the beginning number. What would happen if I did this on the numbers from 1 to 100? I'd get 99. I wouldn't get 100. So we need to tweak that idea just a little bit. Any thoughts as to how I might do that?
So 147 minus 35.
It is minus 35. Why in the world should I subtract 35 and 30 instead of 36? Aside from the fact that it just gives me the right answer. It does give me the right answer, but why? Why should I subtract 35 instead of 36?
Because you're taking out the starting number.
Yeah. So imagine all of these numbers were sort of, in a row in front of you. You've got the number 1, the number 2, the number 3, all the way to the number 147. Was that our number? 147. So what I'm actually doing is I'm removing the first 35 numbers. They're not in my list anymore. That's why I'm subtracting 35. I'm taking off the first 35 numbers and removing them, but 36 is still in my list. Can you picture that? Another way to think about this, if you prefer, and you certainly can, is that you're going to do 147 minus the 36, and you just always add 1 at the end. Just add 1 back in. So if it makes more sense to you to think about it that way, you certainly can. It's the ending number minus the beginning number, and then just add 1, if you want to do it that way. Now, there's a caveat to this I'll mention, but let's finish this one first before I confuse the issue. So 147 minus 35, how many numbers do I have? 112. There are 112 of these. So if I add S and S, I get 2S because I've doubled my count, right? I have double the amount that I started with. What do I do instead of having to add 183 together 112 times? I multiply. So 183 times 112. What is, I don't have that number written down. So what is 183 times 112? 20,496. Oh, I got 2 different numbers.
Sorry, multiplying.
Double check.
I was looking at.
Did it still work out? Okay. That's okay. What's our last step then? Divide by 2. I need to divide by 2 to remove the doubling that I did. So that's 10,000. 10,248? Yeah. Okay. So there's some variations of this that show up in your homework. The variations skip count. So I'd like for you to notice what's happening here. In both of these problems, I'm adding every single whole number together, right? 1, 2, 3, 4, 5, all of them. Yeah? But some of the ones in your homework are going to skip. They'll add like only the evens. It'll go 2, 4, 6, 8, 10, 12. Or it'll add only multiples of 5. 5, 10, 15, 20, 25. Okay, is everybody with me on the difference here? But I'd like for you to think, we'll do it in terms of the evens first. If I were skip counting, I were only adding the evens together. And let's just do the 1 to 100. So there's 100 numbers from 1 to 100. But how many even numbers are there from 1 to 100? There's 50. Right? There's 50. Well, that's because it's half of the numbers. And it's half of the numbers because we're skip counting by 2. Right? So if we were skip counting by, say, 7, we were doing multiples of 7, like 7, 14, 21, 28. We were doing multiples of 7. And I had a list of numbers. What would I have to divide by in order to find how many numbers are on my list?
7.
I divide by 7. Okay, so that's the only nuance that shows up in those. You do need to be careful of where I start versus subtracting off the number at the beginning kind of stuff. But we've already talked about that because the numbers don't necessarily start skip counting at 7. You could do multiples of 7, but start at 21, right? So you have to think about subtracting things off and dividing them properly. Does that make sense? Okay, let's look at another strategy. All right, this one is a fun one. So if you have, if any of you try to coordinate things with athletics, this is a really good example. My son is a part of a rec center, right? He develops things like this, and so this is something that would be near and dear to his heart, as would the soccer in and of itself. So if a soccer league has 10 teams, and each team plays every other team once, how many games will the league manager need to schedule at the start of the season? Now, this is a reasonable question, right? They got to know how many games they got to fit into. They've got to spread it across how many weeks, and they've got to get fields, and they've got to get referees. They've got to get all that stuff coordinated, but it all hinges on how many games do I have, yeah? Okay, so 10 teams makes this very tricky But if we examine a simpler case, like a smaller number of teams, it becomes much quicker at identifying what's happening and how to find that answer. So let's say instead of having 10 teams, we only had 3 teams. Okay? So let's say, this is my simpler option, we only had 3 teams. And so that we don't have to write very much, we're going to call the teams very uniquely A, B, and C. It's unique, it's not interesting, right? Yeah. Okay, so Team A gets their schedule, and Team A's schedule is going to show that A plays B and A plays C. That's what theirs is going to look like. Not a very exciting soccer schedule, by the way, right? Just 2 games. Team B gets their schedule, and Team B is going to show that they play Team A and they play Team C. And Team C is going to get their schedule, and that's going to show that C plays A and C plays B. Are there actually 6 games?
No.
No. Why not? I wrote down 6 things. Caleb?
Because you're still using the same letters, they're just in a different order.
Yeah, and why does that not make sense for this particular context? Sometimes we flip letters and they are unique, but why is this not unique? What does AB and BA mean? It means a game that they're playing, right? That's just one game. So what happened here is that I double counted some stuff. Right? I don't really have 6 games. How many games do I have?
3.
3. Okay, so now let's think about it. Why did I get 6 games to start with? Like, where did the 6 come from? Well, how many teams are there?
3.
3. And how many games does each team have to play? 2. That's where 6 came from, right? 3 teams, 6 games. 3 teams, 2 games each. So I got 6 games. Why did I divide by 2? Right, because that's what happened, right? 6 became 3, it divided by 2. Why did we do that again?
Because they're repeated.
It's okay. What do you have? What was that?
It was the same game.
It was the same game, right? I double counted every game. Agreed? So in essence, what I really did is I took my number of teams, 3, times 2, because that's how many games each team played. And I divided by 2 because I double counted everything because I counted it in both of their lists. Okay, does everybody make sense of what we did with the 3 teams? Okay, extend that idea now. What happens when I have 10 teams? Well, I have 10 teams. How many games does each team play? How many games does each team play? I said that right, yeah. 9. So there's 10 teams, each plays 9 games. Are there really 90 games? No. What do I need to do? I need to divide by 2. Because every game was counted twice. It was counted when I counted one team and when I counted the team they played. Caleb?
I didn't understand how you got there would be 9 games.
Because 10 times 9 is 90. I haven't actually written it down, but I multiplied 10.
Because the team.
Oh, the 9, is that what you're asking
Yeah.
about? I'm sorry, I misheard. Do you want to explain? Go ahead.
Well, the team can't play itself if there's a total of 10 teams.
Yeah. If there's 10 teams, then they play 9 of the other teams because they don't play themselves. Yeah, that's why. Thank you for that. I didn't catch the question very clearly. I apologize. Yeah, so there's 10 teams. They play each of the other 9 teams. And then if you look at the list of games, there would be 90, but that's because it would be on everybody's list, and the list would count every game twice, the total list. So 10 times 9 is 90, which is what I thought your question was. And then 90 divided by 2 would be 45. So we would need to schedule 45, games. Okay, everybody good? Excellent. All right. This is probably one of my favorites. I mentioned last time that you can write equations for things, and that's fine if you want to. And this is a very, very straightforward equation kind of one. Like you could probably see this in an algebra book very cleanly. but we don't need algebra equations to do this. So let's read it together. A store sells bicycles and tricycles. There are a total of 15 cycles in the store. There are 35 wheels on those cycles. How many type of each cycle are in the store? Okay, so if you were in an algebra course, you'd write things like X is the bicycles and Y is the tricycles and X plus Y equals this, and the bicycles have 2 wheels and the tricycles have 3 wheels, and then I've got the total of those things. We could do that. I mean, I'm not asking you to, but in general, could we probably do it that way? Well, yeah, we could do that, but we don't need to. Do you want to see make a diagram for this one? It's very exciting. You're going to get to witness my beautiful skills of drawing. Are you ready for this? Okay, here you go. This is a bicycle. 2 wheels. Okay, everybody good? All right, how many cycles are there? What did it say? There's 15. I'm going to draw 15 of them like they're bicycles. Okay? So we're going to draw 15 bicycles. So you draw your 15 bicycles and I'll draw my 15 bicycles. Okay. There's not 15 bicycles. I mean, that won't work in this problem. It's a good place to start. I mean, 2 wheels on everything. How many wheels are currently on your paper? 30 wheels. Everybody there? We're getting close to there. So if we've got 15 bicycles, we would have 30 wheels. But how many wheels are we supposed to have? 35. So I mean, we're not really physically turning a bicycle into a tricycle, but we are on my screen and on your paper. So we're going to take one of these images that we thought was a bicycle, and we're going to make it a tricycle, just like that. There are 3 wheels on there. That is my tricycle, right? But how many of those do I need? 5. Well, there's 15 total of the objects. I need 5 of them because how many wheels do I need to get? 35, and I'm short 5 wheels right now. So I need to take 5 of my bikes and turn them into trikes, whichever 5 you wish. Can you answer the question? How many bicycles are there? Bicycles.
15 bicycles.
So 10. And how many tricycles? That was the 5. So at the end of the day, the end of the diagram, we can answer this question that I have 10 bikes and 5 trikes. Okay, that's kind of cool, right? No algebra needed. So sometimes I feel like we get overwhelmed when we looked at like word problems with little ones, right? We're thinking like, how in the world would I do that? Like, why in the world is that showing up in this little 3rd grader's textbook kind of thing or whatever? Well, it's probably showing up because there's an intuitive thing like this that they're wanting them to do. Some strategy that clearly didn't involve algebra because that doesn't make sense for the 3rd grader or the 4th grader, right? This would be an example where we can use a diagram to find the solution. Let's try the next one. This is another one that's very commonly going to show up in an algebra textbook. We have 48 feet of fencing, and we wish to make an enclosure along one side of an existing barn. What lengths would the sides need to be to have the greatest enclosure for our chickens? Do any of your families raise chickens? My mother now raises chickens. It's been a very interesting experience. She makes these very long Facebook posts about her chickens. It's all the thing to do. Very excited about her chickens. So we're going to make an enclosure for chickens on the side of a barn, okay? So there's lots of ways to do this too. I mean, there are. But a diagram is a good place to start. And I know the directions don't say we're going to use a diagram, but that is part of what we're going to do. We're also going to roll into this how we can use lists. But ultimately, the process is going to involve guess and check. Okay? It's a very involved problem. Lots of steps. But you'll see how they all work together. So let's draw a picture first of what's happening. We need a barn. So we're going to make a barn over here. Our barn there yet. Now it is. I didn't want to write on my screen for some reason. I don't know. Here's my barn. And I'm going to make an enclosure along the side of the barn. And the enclosure itself is going to have only 3 sides. Why don't I need 4 sides if I'm enclosing along the side of the barn?
Because you're using the side of the barn.
Yeah, I'm using the side of the barn. Can you guys imagine that? If you've only got so much fencing, you're not going to put the fence beside the barn, right? That'd be a waste of your fence. That'd be so sad. Don't waste your materials. So here is our enclosure. It's going to look something like that. It's got just 3 sides. Okay, everybody good so far? Okay, now we know that the lengths here of the black enclosure that I've made are the fencing, and they're supposed to total how much? 48, right? Now, the fencing could look like this, but like it also could look like this instead, right? Or it could look more like a square, you know? It just has to add up to 48 when we're all said and done. And our goal is to do it in such a way that we have the most space, otherwise known as area, inside of it. Okay, so good? I mean, so far so good? Okay. So how do we do that? Well, one of the things you need to remember is some of your features about a rectangle. So what can you tell me that you know about this rectangle? There's lots of things you could say, some applicable, some not. So tell me something you know about the rectangle.
2 of the 4 sides are shorter than the other 2.
Okay, so they don't have to be, but my picture is showing like that they are. Yep, what else?
Right angles.
There's right angles at the corners, absolutely. What else?
2 sides of parallel line.
Okay, the 2 sides have parallel lines, so we have a parallel line to the top and the bottom, or to the left and the right. What about side lengths? Anything you know about those?
Opposite sides are equivalent.
Good. So the length of the opposite sides, they match, right? So if you want to sort of draw it in the way you would have, well, not like that. Kind of like this, right? These 2 are equal. And the same thing would be true on the other side. Those 2 are equal. How about perimeter? What do you know about perimeter of a rectangle? What is that? What does perimeter mean?
All the sides added up.
Okay, so perimeter is the distance around the sides. We get them by adding up all the sides. What about area? Because that's what we're trying to maximize, right? The space inside. What's the area of a rectangle? You guys know this. Thank you. Say it louder. It is length times width. Thank you so much. It is length times width. Okay, so I think there's probably enough for us to go off of. Obviously, the length and the width part is important for this problem because it does ask us about space, right, inside. The opposite sides being equal is going to come into play because the perimeter is part of the discussion because we've got 48 feet of fencing. So all those things we're going to need, and they come from some of the other features you guys mentioned about right angles and parallel sides and things like that. So we're going to make a guess. But we're going to make our guess and keep track of it in a list. Because random guessing and checking, it often ends up taking us a really long time. But if we can keep some kind of a structure and order to it, if for no other reason than to not guess something twice, then we'll hopefully get to the answer a little quicker. So we need to guess side values. The constraint is that the side lengths need to all add up to 48. So I will start us out. We're going to decide that the top and therefore also the bottom are going to be 10 for no real good reason. That's what I picked. Okay? So if the top is 10 and the bottom is 10, how much do I have left for the third side? 28. Okay? And if you're wondering where 28 came from, it's because all those have to add up to 48. Everybody good? Okay? So this is our guess on our side lengths. And what we want to do is we want to check and see what in the world we get for the area. Now we established that the area is length times width. The length and the width here are 10 and 28. So what is 10 times 28? We have 280. Now that may be the actual answer. We don't know. But we definitely are not going to decide that right here and there. We need to guess again and see if we can get something bigger or smaller from there. So I'd like for us to restrict looking at just the 10s because they're going to have to match. So I'd do 2 of them and find the third one. So somebody change the number of 10 to something else for me.
7.
7. All right, let's do 7. So let's try 7 and 7 because the top and bottom have to match. How much will that leave for the third side?
34.
34, you said. Yeah, sorry, I just heard it wrong. 34. Okay. And then over here for our area, I'd have 7 times 34. What's 7 times 34?
238.
Is it? You may be right. Very good. 238. So that guess ended up being smaller than the first guess, right? Guess again. Something besides 10 or 7. 13. Okay, 13, 13. What does that leave me with? How many? Is it 22? 22? Okay, so let's try 13 and 22 multiply. I don't have answers for some of these, so you're going to have to tell me. 286. Ooh, that's better than the first one, right? So that one gave me more area. Now, I started with 10 and I went down to 7 and that did not increase the value, it decreased the value. This one went from 10 to 13. I increased the top and the bottom and I ended up with a bigger area. So that's something to keep in mind, keep aware of as we're keeping a track. It still may be the answer and it may not. So give me another guess. 12. So 12, 12 and what? 24. Okay, so what's 12 times 24? What is it? It's 288. What do you notice? That's bigger, right? So it sort of should seem reasonable that as I make my next guess, I'm not going to make the 12 get bigger than 13, right? Because when I went from 10 to 12, it got bigger, and 12 to 13 ended up going smaller, right? The answer over here, right? I had this value, and if I look at this value, it's smaller if I go all the way to 13, but it's bigger if I went only to 12. We should guess at least one more thing. What do you think we should guess?
11.
We should guess 11 because there is something in between the 10 and the 12 that has the potential that seems like it could be a potential answer. So if I have 11, 11, and what would I have?
286.
Oh, sorry, the side length first. 26. So 11 times 26, 6. And what do I get? 286, which is the same as the 286 I got from the 13s, right? So there's no other space to guess in a way that would get this any bigger. Notice I'm not interested in us using decimals and fractions. We're not going to use decimals and fractions this whole semester. There's one little caveat when we get to coins, but when we talk about some coin stuff. But we're not doing decimals and fractions. That's proportional statistical reasoning, which is another class we do, okay? So this one right here gave us our largest value. Now we need to make sure we answer the question asked. It said, what lengths would give us the greatest area? What are the lengths of the sides? Okay, 12, 12, and 24 what? All right, so we have 12 feet, 12 feet, and 24 feet. Another question it could have asked us that we would do all the same work for is, what's the total area? It could have asked us that. It didn't, but it could have. Okay, we have one more on this page. Yeah. Working backwards. One winter night the temperature fell by 15 degrees between midnight and 5 a.m. By 9 a.m., the temperature's numerical value had doubled from what it was at 5 a.m. By noon, it had risen another 10 degrees to 32. What was the temperature at midnight? So this is a working backwards problem because we know something that happens in the future and we're trying to figure out what happened in the past. Does that make sense?
Yeah.
Okay. So we're going to write sort of down a series of steps of what's being described as happening and then figure out how to work our way backwards in that description. So let's list the time frames that they're talking about first. What's the earliest time that's mentioned?
Midnight.
Yeah, it's midnight. What's the next time mentioned after midnight?
5 a.m.
5 a.m. And then what? 9 a.m. And then noon. Okay, does that make sense? Okay, so let's describe in some sort of mathematical notation what is happening between midnight and 5 a.m. From here to here. What does it say it did?
It falls.
It did what?
Increased.
It increased. Does this one say it increased or decreased? This one was decreased. So this one is that it decreased 15 degrees. What happens between 5 and 9?
Just didn't double.
It says that it doubled. The reason it says that it doubled the numerical value is because we have 3 temperature scales. Are you aware of that? Fahrenheit, Celsius, and Kelvin. So we want to stay focused on the numerical value within whatever system we're looking at. That's the reason for that nuance in language. What happens between 9 and noon?
Sorry, it rises 10 degrees.
Yeah, this one is where it increased. So it increased on that one 10 degrees, 12 degrees, 10 degrees. Okay. And we actually know what the temperature is at noon. What is the temperature at noon?
32 degrees.
32 degrees. So if the temperature is 32 degrees at noon, and it increased 10 degrees to get to 32 degrees, and we go backward, what was it before it increased 10 degrees to give me 32? 22. So going backward here, we would go up to here, right? We would be subtracting the 10 degrees, and we would be at 22 degrees. But it doubled to get to 22 degrees. So if I go backward, what would I have to do in order to figure out what it doubled from to give me 22? Divide by 2, and I would be at 11. Ooh, 11. Sorry, it's all a little bit wonky because I've got these arrows going on, but we're at the 5 a.m. right now. I need to go from 5 a.m. back to midnight. But from midnight to 5 a.m., it decreased 15 degrees to give me 11 degrees. So what would have had to have decreased from to give me 11? 27. And how did we get there? Whoa, sorry. We added 15, right? 37. Are you guys saying that because no, 27. I wrote it right, didn't I?
It's 26.
26 is our 15. Oh, because I was looking at a different number. I'm sorry. 26. There we go. 26. We added the 15 degrees to the 11 degrees to get to the 26. I was looking at the 22 below when I was thinking about my 2. All right, so the question asks us, what was the temperature at midnight? And what's the answer? 26 degrees. Now, it doesn't actually say Fahrenheit or Kelvin or Celsius. It's got to be Fahrenheit for it to make any sense here, but it doesn't say that, so we're just going to leave it as degrees. Okay, let me talk about what's happening next and then tell you how we're going to handle this because we're at the end of class enough that we don't have time to do group work. But I want you to do group work, especially for this first one. So let's actually talk about what's on the next page, and then we'll talk about the group work situation. So, have you heard of the 12 Days of Christmas before? You heard the song? The first day of Christmas, my true love gave to me, right? Okay. So the 12 Days of Christmas all actually hinges on religious symbolism. The 12 comes from the different parts of the Bible. And so this is a really cool feature. And so I want to walk through this with you because there's an example, in part anyway, because there's an example in your group work questions about the 12 Days of Christmas. And I want you to have a list of what gift comes on which day, because there are different versions of the 12 Days of Christmas. We had a children's book in our house once that did it out of order of what I had learned and what I knew to be accurate from songs. It was very strange. But I want to make sure you have the same list as everyone else. So these are the 12 Days of Christmas. So my true love, right, the partridge in the pear tree, true love is representative of God. The 2 turtle doves are the Old and the New Testament. The 3 French hens are faith, hope, and love. 4 calling birds are the 4 Gospels, Matthew, Mark, Luke, and John. The 5 golden rings are the Pentateuch. Do you guys know what that is? first 5 books of the Old Testament: Genesis, Exodus, Leviticus, Numbers, and Deuteronomy. That's the Pentateuch. Those are the books that we share with the Jewish faith. That's the Pentateuch. So, the 6 geese of laying are the 6 days of creation. 7 swans of swimming are the 7 gifts of the Holy Spirit. The 8 maids of milking are the 8 beatitudes. The beatitudes are blessed. The blessed be the poor in spirit, blessed be the pure of heart. What are those? The 9 are the 9 ladies dancing are the 9 fruits of the Holy Spirit, right? Faith, hope, love, all those kind of ones, all that stuff. Okay. The 10 lords of leaping are the 10 commandments. The thou shalt nots, right? Thou shalt not have any other God before me. Thou shalt not murder, things like that. The 11 pipers piping are the 11, did I skip it? No, I didn't. The 11 faithful apostles. So we take our apostles and we subtract off Judas because he wasn't faithful. 12 drummers drumming are the 12 points of the doctrine of the Apostles' Creed. There was a song not too long ago that came out that says, I believe in the Holy Church, and I believe in the virgin birth, and I believe that's the Apostles' Creed put into a song, if you're familiar with that at all. So these are our 12 days of Christmas. And the question that you're going to be encountering in your group work, which we will do next time, is that it will ask questions like, how many geese a laying did we get? Or some variation of that, right? Well, the geese a laying, which one was that? Is 6 days of creation. So it's a 6 geese a laying. So you get 6 geese a laying, but you don't get them on all 12 days. You don't get them until day 6. But you get the 6 geese of laying on day 6 and on day 7 and on day 8 and on day 9. You know what I'm saying? Every year somebody goes through and tries to figure out what the total cost of the 12 days of Christmas would be this year. Did you know that? It's a thing. Like, there are people who calculate this out with costs of inflation and stuff. Yeah. Okay, so, and then it'll ask you a question. There's going to be a question something like, which gift did we get the most of? Well, I'm going to tell you what, it's not the partridge in a pear tree, because you only get one of them. You get them for all 12 days, but you only get one every day, so you're only getting 12 of those guys, right? Okay, so it's something in the middle. Got to be something in the middle, because you got to get a bunch of them every day for as many days as possible. All right, so this is what's going to happen on your group work.